You already know about these distributions from the probability course. Now I am going to teach you a few more distributions in this class. One of them is the log normal distribution. Okay, so log normal distribution means this, the logarithm of which is going to be normally distributed. So log normal random variable is a random variable. When you take the logarithm of this random variable, you are going to get a normal random variable. For example, if y is normally distributed, then if you define x as e to the power y, then x is going to be log normally distributed. Again, it is going to have the location and the scale parameter mu and sigma square. However, the expected value of x is not mu and the expected value of x is not sigma square. They are just the parameters coming from the original normal distribution. And the log normal distribution, my friends, is used for financial simulations. For example, to model the rate of return. The rate of return of an investment is modeled by a log normal distribution usually. And why? Because just like the normal random variable can be used for modeling the sum of random components, log normal random variable can be used to model the product of the random components. So according to the central limit theorem, the sum of independent random variables is normally distributed. This means the product of independent random variables should be log normally distributed according to the relationship between the normal and the log normal random variable. And you know, the rate of return of an investment is dependent on every effective task on that investment, and every effective task is multiplying the previous return with a value that is either greater than 1 or less than 1. Okay, so when you perform a task, the task is going to add a value to the product that you are developing by multiplying it with a value that is distributed around 1, and if it is a value adding task, then it is going to multiply it with something greater than 1. So if you consecutively multiply a value with random factors which either increase the value of the product or decrease the value of the product, then in the end, the rate of return is going to be the products of these factors. By the way, log normal random variable is non-negative. Why? Because if you take the exponential function of anything, it should be non-negative, right? E to the power of something can never be negative. And what kind of shape it has, as you can see, it can be never negative. And the distribution looks like the gamma distribution. So we start from here. We do not have a left tail. We start from 0. We start in a convex shape. Then we have a shape that looks like the normal distribution. However, not exactly like normal distribution, because as you can see, the right tail here is much more skewed than the left tail, and it converges to 0 in a slower manner. So the log normal distribution is not a symmetric distribution because of the left tail ends at 0. However, if you, for example, increase the mu value and decrease the standard deviation, okay, if the standard deviation in the original normal distribution goes to 0, it is going to look like the normal distribution. So as you can see in this black example, it seems much more symmetric, right? So as the sigma parameter gets closer to 0, then even if you take e to the power of y, it is going to look like the normal distribution. So gamma distribution is another distribution which is one of the most flexible distributions to model non-negative random variables. So if you have a data with non-negative observations, gamma distribution can be a very good candidate to model it. Why? Because it is very flexible. It has two parameters, shape parameter and the scale parameter. The shape parameter is called beta, and the scale parameter is called theta. And you see, when the shape parameter and the scale parameter is equal to 1, you get this black line as the PDF. So which probability density function does it look like? It looks like the exponential distribution, right? because the exponential distribution is actually a spatial case of the gamma distribution. When the parameters, shape and scale parameters of gamma distribution is equal to 1, it becomes exactly exponential random variable. And for different parameter settings, sometimes we can have a function which starts concavely and peaks at one point and then converges to 0 and it gets convex. And sometimes it looks like the log normal distribution. Again, it starts convexly, then becomes concave and peaks at some point, and again it converges to 0. And if you increase the shape parameters sufficiently enough, it is going to look like the normal distribution. So anything that can be modeled by normal distribution can also be modeled by the gamma distribution as well, because gamma distribution is capable of imitating the normal distribution. And because of that reason, gamma distribution is much more flexible in modeling random variables than normal, because normal distribution has this problem. It is symmetric. And sometimes it can admit negative values. It has these problems. However, the gamma distribution does not have these problems. It can never admit negative values, and if the shape parameter is large enough, it can also imitate the normal distribution. It can either be symmetric or it may not be symmetric. It may even look like the exponential distribution. So because of that reason, gamma distribution is a more flexible distribution to model continuous random variables. Other than gamma distribution, we have the Erlang distributions. And actually, Erlang distribution is a spatial case of the gamma distribution. In the gamma distribution, if the shape parameter takes only integer values, then these gamma random variables with integer valued shape parameter are called Erlang random variables. So Erlang random variables are spatial cases of gamma random variables where shape parameter takes integer values. In this page, you have the Erlang random variables. As you can see, when beta is equal to 1 and theta is equal to 1, it is the exponential random variable again. This is the case where beta is equal to 2 and theta is equal to 1, and this is the case where beta is equal to 3 and theta is equal to 1. So Erlang random variable is actually what? Erlang random variable is the sum of exponential random variables. For example, if the interarrival times of clients into a bank is exponentially distributed, if the time between consecutive arrivals is exponentially distributed, then the time between every fifth arrival, the time between the arrival time of every fifth client, I mean the fifth client, the 10th client, 15th client, 20th client, so on and so forth. The time between these arrivals are going to be Erlang distributed, where the scale parameter is the inverse of the rate parameter of the exponential arrival rate, and beta is going to be 5. So beta here, in the Erlang distribution, the integer valued beta parameter is representing how many exponential random variables we are adding up. And theta, the scale parameter, is basically the average time between the arrivals, which is 1 over lambda. Remember the exponential distribution, the average time between arrivals was 1 over lambda, the inverse of the rate parameter, and theta is the average time between the arrivals, and beta is how many clients we are counting. So Erlang is the time between the arrival of every beta client. Now you see the parameters must be positively defined and beta must be a positive integer. Again, it's a flexible distribution, however, with only integer valued shape parameters. And beta distribution is even more flexible than the gamma random variable. Beta is one of the most flexible distributions in probability theory. And when you, for example, use ARENA input analyzer, and if you, for example, transfer a data there, most probably ARENA is going to give you a result with beta distribution. It is going to fit either a gamma distribution or beta distribution. That's because beta is the most flexible distribution which can imitate any type of histogram as long as it has a shape looks like there is a peak, and around the peak the function should be concave, and as it converges to the tails, it must be convex and converging to 0. In that case, if you have a histogram that looks like this shape, either symmetric or not symmetric, beta distribution can be a good distribution to model it. It has two parameters, beta 1 and beta 2 in beta distribution. Originally, with just these two parameter settings, the beta random variable can be distributed between 0 and 1. Okay, the beta random variable is actually originally is distributed between 0 and 1. However, just like you scale random numbers and shift them to convert them into uniform random variates, you can also scale a beta random variable and shift it, just like in generating a continuous uniform random variate, just like here. You can also expand the beta distribution into another interval. For example, this is 1.5 and 3 interval. And how did we get that? You know, the width of this interval is 1.5. So we multiply the beta random variable with 1.5 and we scaled it, which is 3 minus 1.5 here. And then we shifted it to move the density from 0 to 1.5. So here, the scale b minus a here is 1.5, and the shift a is also 1.5. In the red case here, we have beta distribution again, with beta 1 being equal to 6 and beta 2 being equal to 3. And here, there is only a scale factor, which is b minus a is 1.25 and a is 0. So you can basically move the beta distribution from one location to another. So b minus a becomes the scale value, and a is going to be the shift value, and we have b beta 1 and beta 2 as well. By the way, my friends, beta random variable is related with the order statistics of uniform random variables. I'm not going to explain this detail to you. Maybe in the textbook it is explained. However, you can also read the Wikipedia or about the beta distribution to learn more about it. Actually, my suggestion to you is to read the Wikipedia pages for all of these distributions, okay, because they give very, very interesting information. So they give information about these distributions which you do not know. Really, I mean, they are like related with each other so much. Each distribution here are related with each other so much. However, we do not have enough time to explain these relationships. We are trying to tell them as much as we can, but you can read Wikipedia pages about these distributions to learn more about them. And Weibull distribution is used for modeling the time to failure for components. So for example, there's a machine, and this machine is going to work for an amount of time until it breaks down. The time until the first breakdown is a time which can be modeled by Weibull distribution. Now, you know, in probability theory, I think your lecturer should have taught you the memoryless property, and exponential random variable is a memoryless random variable. And there are some devices in real life which have this memoryless property, which means even though you use that device for a very, very long time, the remaining lifetime has the same distribution as a newly purchased product, which means even though you use that product, this product never gets tired. I mean, the human life is not like that. You know, if I tell you what is the probability that a newly born person to live more than 50 years, and if I ask you what is the probability that for a person who is aged to 80 to live an additional 50 years, you would definitely say the first one has a larger probability, right? The human body gets tired. I mean, as you breathe, the human body gets tired because of oxidation. Oxygen, this is a necessary concept for you to live, but oxygen is also burning your body. It is tiring your body up, and that is the reason why we die eventually. So to live, we need to die. That's the case. And because of that reason, the human body is not memoryless. However, there are some devices like light bulbs or electronic devices which have the memoryless property, And if the lifetime of a device has the memoryless property, then it should be modeled by the exponential random variable. Now, there are also some devices or machines which do not have the memoryless property. For example, an automobile. I mean, just like the human body, if you continue to use an automobile, after some point, it is going to break down itself. I mean, it is going to get too tired. Either the tire is going to explode or something is going to happen to that eventually, right? So because of that reason, my friends, Weibull distribution is another distribution which can model the time to failure for components. If it does not have memoryless property, it can model the time to failure for components. Now, you can easily see here there is a red line. In this red line, we have the location parameter as 0, the scale parameter alpha is 1, and the shape parameter beta is 1. So when the location parameter of the Weibull distribution is equal to 0, and both the scale and the shape parameters are equal to 1, we have the standard exponential distribution here. And if, my friends, the scale parameter is different, again you have the exponential distribution, which means Weibull distribution also covers the exponential distribution. If you define the location parameter as 0 and the shape parameter as 1, whether the scale parameter is anything, any positive value, you will always get an exponential random variable. So Weibull distribution can also model the memoryless devices, because in spatial parameter setting, it also has the memoryless property, just like the exponential distribution. And finally, my friend, if you do not have enough data to identify a model, or if you cannot find a specific model in these candidates, if you cannot find a specific model by the goodness of fit test, then in that case, what you can do is to use the empirical distribution and generate random variates from the empirical distribution, as you have done in the last chapter. But please do not forget to consider the physical characteristics of the process when selecting distributions. If you are modeling the time to failure of a certain machine in a production system, for example, or a maintenance system, then Weibull is the candidate there. Okay, try to find something with Weibull distribution. Do not try to find something with other distributions. Or if you are trying to model the service time, try to find something with normal distribution or at least gamma distribution. Or if you are trying to model the inter-arrival times, try to find something with exponential distribution or a non-homogeneous exponential distribution where the rate of arrivals change through the time. But most probably it is going to be exponential distribution. Now, you also need to be careful to answer this question. Is the process discrete or continuous? I mean, you need to check the data itself, and by looking at the data, you need to define if the process is discrete or continuous values. And also, you need to determine if the values are bounded or not. Is there a natural bound to the values? For example, you know, the time to failure has a natural bound. It can never be less than 0. I mean, there cannot be negative duration. So it has a natural bound there. Or a percentage value. It has a natural bound between 0 and 100. Percentages can never be greater than 100 and can never be less than 0. It has natural bounds. So you need to also identify these things in observations as well.